Who is aware about integral science in this room? Okay, so not a lot of people. Basically, we are a media evaluation company. We help our clients to evaluate quality of ad campaigns. Oh, something is happening. We essentially measure three parameters: brand risks or brand safety risks, viewability or engagement with ad, and fraud, suspicious activity. And our clients basically trust us to qualify and measure their ad campaigns online. We wrap their creatives with our own JavaScript, and each time this creative is displayed anywhere in the internet, we receive multiple signals from our JavaScript. Those bring additional information for us, like about fraud, about different performance statistics, etc., etc. And this actually causes very interesting workload levels. We can reach up to 1.5 million of signals or messages coming into our systems per second. And those data form quite considerable amount of volume. We observe up to 50 billion events per day and up to 20 terabytes of data ingested daily across all our data centers. Originally, we used Hadoop, and we used Hadoop MapReduce to produce reports. But there were a few reporting issues. Basically, Hadoop is allowing you to execute any arbitrary job. So it's very tricky to predict when your data, when your reports are going to be ready. So we started to look into alternative solutions. And the idea was to migrate to sort of real-time technologies, stream processing technologies. Because stream processing enables you to control your data processing latency explicitly. On each stage of processing, you know how much delay you actually introduce into the system. Or at least you can approximate this delay. So your reports, your data are ready with predictable latency. Another driver was closer integration with real-time bid exchanges. If you are familiar with ad ecosystem, somebody can spend like thousands of dollars on media, on RTB exchange in a matter of minutes. So our previous daily reports were not very good thing for a lot of clients. And we were looking to improve our data turnaround time. And the third driver was actually a very interesting one. We assumed, and as it was proved, we assumed correctly, that Hadoop is not very good, specifically MapReduce is not very good way to handle our use case. It is an I/O disk bound system. And as such system, you unavoidably do a lot of buffering. So if you avoid these disk I/O operations by some way, you can get a lot of performance improvement. So let's take a look onto typical log event processing pipeline or event processing pipeline. It actually covers not only our use case, which is web data analysis. It covers Internet of Things, healthcare, web analytics, advertising. You basically have a series of operations like normalization or transformations, SESSIONIZATION, enrichment, some filtering and aggregation. SESSIONIZATION is a pretty interesting one. In real world, and especially in our case, single event happens, but we get multiple signals, multiple HTTP calls into our system. And it turned out that our active data set for SESSIONIZATION basically joining by correlation ID, was not very large. If we assume session length of 15 minutes, it's approximately 1.3 terabytes of data. But it's like a topmost estimate. It's a large volume, but if you split it between servers, it turns out it's around 27 gigabytes per server, which is manageable. You can easily get a server with 100 gigabytes of RAM these days, or even more. Enrichment. This is fairly frequent and easy operation, right? You have some reference data which you want to bring into your data and you basically join with dictionaries. In many cases, and in our especially, it is very limited amount of data, a few gigabytes in our case. Aggregation is a different beast. Potentially, if you are building OLAP cubes in memory of your system, they can grow very huge, but there is kind of limitation on their size. They should be comprehensible by a human. And that means they won't grow that much. In our case, they definitely don't. So, when we started development of this system, real-time or in-stream processing was definitely about LAMBDA architecture. Who is familiar with LAMBDA architecture? Okay. So the idea of LAMBDA architecture is quite simple. The hypothesis is it is very, very hard or even impossible to build real-time stream processing system which produces data with low latency, but at the same time gives you reliable and precise data as output. So it's suggested to use two layers in the architecture. It's suggested to use speed layer, consisting from stream processor and some sort of real-time database, and batch layer, which is usually defined as Hadoop. Hadoop runs like hourly, semi-daily, or daily, or weekly, and produces precise and reliable results. Speed layer runs fairly quickly and updates the data fairly quickly, but nobody kind of trusts it. There is a special kind of query layer which merges this data. And as part of our POC, we actually have built such architecture. We estimated that number of servers we needed for real-time stream processing was around 50 servers. And unfortunately for Hadoop, we needed 300 servers to do the same stuff. Well, there are multiple reasons for that, not only increasing effectiveness of data processing, but actually optimization of the code done as part of the POC. But all in all, the first reaction of my boss was something like that. Well, I can definitely understand concerns regarding that kind of spendings. How could we lower costs associated with such kind of architecture? First of all, speed layer, batch layer, each of them requires separate set of routines or code base, right? So you need to deploy it separately, you need to monitor it separately, you need to test it separately. Yes, there are tools, those allow you to do it in a single place, right? And then translate your code into a real-time environment and into an offline environment. But unfortunately, it still means you have to do testing, you have to do development, you have to do monitoring, and you need twice more brain power to take care about such systems than your Hadoop. Also, as you have seen, it does not make a lot of sense to use like a lot of redundant hardware to do the same thing, one quickly and one slowly, but reliably. So we started to look into so-called KAPPA architecture. It is promoted by people behind Kafka, Confluent. And the idea is that you basically do all stuff, all your data transformations in stream processor of any sort. It can be Spark streaming, it can be Storm, which we used, or any other tool. And you use your input message broker as a sort of system of record. So how does it work? You read just very small batch of data from Kafka or message broker, process it, and write out result to some persistent storage. Write checkpoint, and then repeat. So you kind of moving through your data stream in small steps. And if something goes wrong, like you're unable to write to output a database or network fails, any error, you roll back to previous successful transaction or micro batch. Unfortunately, there is a problem here. Previously, I mentioned operation which is called SESSIONIZATION. Session is essentially a group of correlated events, those connected with some sort of correlation ID or real-world event ID, and those happen in specific amount of time from the first event of the session. This is the simplest definition of a session. And actually, we have a more complicated definition of session, but for the sake of discussion, let's assume that session is a fixed period of time from the very first event coming into the system related to specific correlation ID. And there is a huge problem with sessions. First of all, they span multiple micro batches. So as part of any micro batch, you cannot say, this is session, I have all data for the session, I can write down aggregated results. And another problem is that session boundaries actually overlap. There is no point in the input feed where we can say, we successfully processed input until this point. Our micro batches just became interdependent from each other. And this is why we need to introduce state processing. We need to have to store state between transactions. And that means if we lose this state, we corrupt our output data. Well, turns out there is a solution. You can use a persistent external database. And we tried to use Cassandra for the matter. Actually, we achieved considerable performance with Cassandra. But again, we needed like 50 servers for stream processing and 50 servers for Cassandra, which is definitely better than 350, but still, you use a lot of hardware just to provide your guarantees, like your reliability guarantees. Well, this was my reaction this time. It was okay for business. Any questions regarding this part? Yes?
How do you make sure that the events which are taken from the Kafka queue into your processing engine are actually in the same one as what it was saying?
Could you speak a little bit louder?
So typically when you are activating on the Kafka queue into your stream processor, the events get reached there and they get sorted based on the time they need. But if you want to actually sort them based on the time they will occur?
We don't need to sort it. And I will cover this in the next few slides. It's actually the biggest challenge of the stream processing, right? Ordering of the events. So, how we can improve this solution? There is a pattern, architecture pattern called event sourcing. Basically, the idea is that your state is discardable. And if you need to recover, you just replay your data from your system of record or your feed manager, feed repository. It is fairly widely used in financial industry. And in order to achieve that, we basically did this. We defined all our transformation and all our state generation functions as idempotent. So if they run multiple times on the same data set, they produce the same state and the same output. But in order to make this work, you need to have reliable storage, which is Kafka for us. We enabled replication there, right? And we started to monitor it very, very closely. This is our system of record. This is our database now. So our pipeline became something like that. And if you are familiar with Spark streaming, you probably have seen something like that, right? Your input topic is input for some function which produces state. Then this state is input for the following stage processing. And then eventually you reach out output database, which is used to source the data. So in case you need to recover after state loss, for whatever reason happened, you basically can rewind your input data stream back for like twice length of the synchronization window or twice length of aggregation window and reprocess all your data. So you get the system like this, and this is essentially a very elegant solution because you don't have excessive dependencies. You don't have external database to manage. You have only Kafka broker, which you need to have anyway. You have stream processors, and you have aggregation layer. And all your data are going through the same code path, right? Either it is for a recovery or it is for normal processing. The data are bound to be the same. The result is bound to be the same for this system. Turned out, and this is very important, I think, that replay of input data stream is several times faster than recovery from external storage. I'm not ready to give you exact numbers. We used Cassandra cluster with SSDs, different configurations, a lot of experimentations, but by the end of the day, replay of input data stream was from 2 to 7 times faster, depending on external, face of the moon, basically. So we went with this solution. We maintain state in memory and recover it from Kafka if needed. So, does anybody see a problem here? Yeah.
I have a question here. So, like, you use the Kafka to replay that, right?
Yes.
But, like, for example, you have multiple source of data and you want to do correlation. How do you manage that? For example, some data could be past data you wanted to correlate, not the data which is happening at that moment of time. Now you don't have the persistent there, but how do you try to correlate to different events?
Well, the thing is, you can control speed of processing of 2 data sources. I will touch it briefly at the end of the presentation. If We actually can talk after the presentation. It's very huge topic. So, are we all set? Who thinks there is a problem with the approach? Okay. What is?
I just have a question.
Yeah.
So when do you acknowledge Kafka now you're done with that event?
It's a sort of pattern. If you use Kafka to write checkpoints into zookeeper quorum, right? You can use Kafka's bookkeeping facility, but you essentially write, position of the last successfully processed message into zookeeper quorum, which is kind of not the best way to do it, just to be honest. So there is a problem here with this approach. It's half of the presentation left for discussion of the problem. So, any ideas? We were talking about pure state generation functions, right? They must not have side effects, but they should be idempotent, right? If they receive the same input, they should produce the same output. And turns out this is not true for sessionization. If we go with a naive way to sessionize events, to join them into the sessions, you basically build something like that. Take timestamp of the first event, add up maximum length of session, and you will get a threshold. As soon as your system clock goes through this threshold, you assume the session is closed. You won't receive any events from this session, right? Or you will discard it. But it's an input to our synchronization function, and it's not idempotent anymore. If you will run it twice, you will get different results based on current system clock. So assume system clock was 12 p.m. when we started to process our data stream, right? And it was 12:30 when we observed state loss in the system. We will roll back or rewind the input stream back. But system clock will show 12:31, right? And all sessions, those reside in these micro batches in the log, will be closed already. They won't be processed. They're out of time. Like, only first event will come. It is, session is closed already. It's emitted into output. You basically will corrupt your data. And so you need to come up with some different approach for that. You cannot use your system clock, your world clock, as a source of time during stream processing if you use any sort of replay. Because, as soon as you rewind your stream, you're screwed. Or if something happening with the system like overload, it is not working anyway. So we need to construct something different. Here you can see a graph representing log produced by a single publisher. At the horizontal axis, we have log position. On vertical axis, we have sort of virtual event timestamps. The server produces events, time is going, and event timestamp is growing linearly. In the perfect world, everything is going to be simple as that. Unfortunately, we have a distributed system with multiple event publishers, with multiple event producers. And it's going to look something like that. So we have multiple publishers, each of them producing events with time and buffers them before sending it to the broker. And this shape actually indicates that all the servers commit their buffered batch then, for moment one, then the next moment, then the next moment. If you take a look into real data, it's almost like that. Your data, while a little bit noisy, going up in small steps. On a micro level, though, you see all of this noise. Plus, you can see these huge spikes. Those can be explained by multiple reasons, as well as down spikes. But typically, this is associated with some servers started to send data fast, before all others, or they have unsynchronized time, or their network is slow just a little bit. And we need to work with that. We need to introduce some sort of logical time, a notion which defines which is current processing time of the system. If you take a look onto this graph again, on a larger scale, logical time or event time is growing monotonically. But on smaller, it's very noisy. So we can use cumulative maximum of observed timestamp as a sort of logical clock, right? So our event processor absorbing incoming data stream and computes maxima of all observed timestamp. And he thinks that if if the event processor have seen 12:30 p.m., the whole system is processing 12:30 p.m. right now. And if we will look into our rollback rewind exercise again, we will see that after rewind, this definition of logical clock will give you the same logical time. Any questions regarding this part? Just for sake of this discussion, let's introduce a notion of cutoff threshold. As we discussed, in our case, we define session as a limited and fixed time window since the first session event. So cutoff threshold is a timestamp of the oldest open session. Timestamp of the session for which we still want or expect to receive any data. And here you can see cutoff threshold as a solid red line, right? We take current system's logical clock and subtract specific amount of time, our sessionization window, and get this line. The problem is that if we observe data coming into the system below this cutoff threshold, we actually lose data. We receive data those we did not expect to receive, and we cannot do anything valuable with them. In order to fix this, we actually can increase size of the session. We can try to fit all these spikes down into session window. But that gives us a few disadvantages, a few problems. While it causes few drops of corrupted sessions, it causes high memory consumption. You basically store data for a longer period of time. You increase your end-to-end latency because you cannot emit data until you waited for the period of the session. If you have synchronization period of 30 minutes, your minimum latency is 30 minutes. If you have synchronization window 1 hour, your minimum system latency is 1 hour. On the bright side, larger or longer sessions give you smaller output time variance, which is kind of useful for aggregation, for downstream aggregation. Size of your active data set for all up cubes generation is far smaller. Also, it turned out you can use different approach to logical time. When we started this project, this information was not available, but sometime later, I think a year later, Google published their data flow white paper. And they suggested to use minima of batch as a logical time. And these two approaches have pros and cons. With our definition of logical time, we basically able to control resource consumption and latency, but we can observe data loss. If you use minimum observed timestamp, you have lossless processing, but uncontrollable latency and uncontrollable resource consumptions. And so we decided quite confidently to go with maximum, cumulative maximum observed event timestamps. This is basically because we can allow ourselves to lose data. In like 0.1% of sessions, we observe these spikes down. And we are okay with that. But there is another problem. Unfortunately, we are short on time, and I will try to touch it briefly. There is another issue. Those can be observed in such systems. When we built it, we kind of assumed we have equal servers. We have even data distribution across our cluster. We will have the same speed of processing on every server in the system. And it turned out to be true for normal processing. But for transitions like scale up of the cluster or scale down of the cluster, or addition of a new broker or misbehaving network, this is not true. So you have to deal with that somehow. Because this causes different logical time on different cluster nodes. And this is a huge problem because a rogue broker going through the data faster will corrupt our time, will shift our logical time to the top, to the upper direction. And we have this large, huge data loss area under the cutoff threshold. Global synchronization is a thing we try to avoid. So we came up with this idea. Essentially, we used a notion of whiteboard. When each of the servers in the cluster writes its time into in-memory data grid, cache, whatever, we used Redis as a temporary solution. And on the next stage, on the next transaction or micro batch, it takes time of all servers in the cluster, add up limit And if any of the servers is going beyond this limit, he basically cut it off, not allowing faster servers to progress faster than the rest of the cluster. Unfortunately, this is performance hit for us, but it's unavoidable. We can actually turn it off, turn it on during system operations. Before we go into maintenance mode, we turn it on, then turn it on. So our final architecture is basically so-called KAPPA architecture. We have approximately 50 servers across multiple data centers. Those run Storm, Apache Storm, and Kafka. Each of Storm workers maintains its state in memory of JVM and has independent logical clocks, logical time computed. Plus, it has its own replica of input data. One important thing to consider is, and I would like to stress it for in-memory and especially stream processing system, is that you need to monitor it extensively. While our system have very high throughput, our monitoring system has very high throughput. We produce approximately 150,000 data points per second across all data centers. And the biggest problem, one of the biggest problems with this system was actually scaling of monitoring, not the scaling of the processing system. And we have a few problems. Those we try to address, but I think it is good to mention them. First of all, sometimes we hit uneven data distribution. So one of our servers is burning, the rest of doing nothing. And Storm actually has very simple scheduler, which do not allow you to redistribute workload or do it not in the best way. And actually, I know a guy from Google who spent like 3 years building a scheduler for their data processing system. So it's a big task to solve, unfortunately. It turned out that loss of state is very non-trivial to detect. And Storm and other stream processors don't help with that too much. Hardware. While we use standard hardware for our system, I mean standard across our company, we hit much more issues than any other department, including Hadoop, because we utilize it like close to 100%. And if you can allow yourself to buy good network hardware for stream processing, do it, because otherwise you will observe very, very strange behavior. Well, and one small thing, actually, we were capable to overload Zookeeper quorum multiple times. So try to avoid relying on Zookeeper for very fast operations. It's basically write limited. So just to summarize. Recovery of in-memory state and through event sourcing is more cost efficient than LAMBDA architecture and any sort of persistent storage to use. Typical log processing can be fit into memory of cluster, especially modern clusters. You don't need to introduce Hadoop for that, in many cases, unless you have correlation. And we built KAPPA architecture and we use it in production, and we believe it's the most reasonable way to go with data processing. Plus, you need to keep in mind that time in a real-time system and in streaming system is the most complex thing to take care about. So keep an eye on it. Any questions? Yes.
Do you have any best practices on how to deciding the batch even for each particular when you actually I mean, 10 seconds, 20 seconds, or Windows seconds?
Sorry, could you speak a little bit louder? I don't hear you.
Yeah, I'm just curious to know how do you decide the batch processing for the stream? When you read the stream, how many elements you read from the stream or time? You read by time and how do you is there any thought process you have or any reason to decide that?
So how we decide to use real-time processing versus batch processing?
No, I mean, when you read the stream, how many records you read from the stream? I mean, is that one by one or you read small batches, micro batches? Or you have this slide where you show that Windows size of each window. How do you decide the Windows size?
Oh, yeah. So how we choose window size for sessions, right? Well, we did our research, basically. We ran with different window sizes and measured loss in precision of our measurements, right? Technically, we could go with this Google's approach, use minimum. Then we won't have any data loss at all. But it's not required for our case, and especially take into account we have like real-time components in the system, like fraud detection, right? So loss of precision on this, like 1,000th of, oh, 1,000th, it's too big. I probably misled you. So probably 1/10 of 1,000, 1/100th of 1,000 of events does not make a big change for us. So we basically measure data precision loss and decide this is 15 minutes. We will go with that. Okay, I'm going to be available if you have any questions you'd like to discuss. I'm here today and tomorrow. Thank you for your attention.